Hi everyone and welcome to Elsa's channel. Today we are going to show you how you can use STK to operate a rendezvous operation between two satellites in the same orbital plane. As you can see on this figure, our two satellites start with a difference in true anomaly that can be seen as the angle marked phi. Our goal is to reach a phi value equal to 0, so to speak the same true anomaly as our target. To achieve that, we will put our interceptor into a phasing orbit that you can see in red, but we have a shorter period than our initial orbit, making our interceptor move faster around the Earth than its target. This is governed by Kepler's third law, which enunciates that an orbit with a shorter period is an orbit with a smaller semi-major axis, and can be illustrated by the formula on the right of the screen, with A being the semi-major axis and T the period. Both are proportional to each other. So if we want a shorter period on the interceptor orbit, we'll simply have to reduce its semi-major axis. To reduce the semi-major axis, we will need to lower the satellite's energy, or in other terms, slow it down. We will achieve this by performing a retrograde burn. Now, why do we want to have a smaller period? Well, by having a smaller period, we will be able to do a shorter in time revolution around Earth and time it in a way where we will be able to catch up with our target. At this moment, we can do the opposite of the first maneuver, burn prograde, and put ourselves back into our initial orbit with only the true anomaly changing to the value of our target. The period of our phasing orbit must be equal to the time it will take for the target satellite to come back to the initial position of the interceptor satellite. This duration can be calculated by dividing the angular section the target needs to cover to get to the position of our interceptor at the time of its maneuver by its angular speed. That's what you can see here with phi travel and little omega target, where phi travel equal 2 pi minus phi initial, the initial difference. Phi initial being the delta between the true anomaly of your target and your interceptor. So target true anomaly minus interceptor true anomaly. Now we're going to calculate all that in STK, use Astrogator, and find the correct maneuver to do to reach this phasing orbit, and then to put ourselves back into a circular orbit at the same position as our target. Now that we have studied the theory, we will practice it by creating a new scenario that we will call Coplanar RPO, and we will keep the default start and stop time. It doesn't matter if you have different start and stop times, it won't affect your scenario. And once your scenario is opening, you will see a window prompting you to insert a new STK object. So you will select the satellite object and select the insert default method and click 2 times on the insert button and close this window. If you don't see this window, you can click on insert here and click on new. You can go to the object browser and you'll see your 2 satellites here, and you will right click on the first one to click on the rename button and rename your satellite target, and the second satellite will be renamed Interceptor. You can double click on the target satellite. You can see that our propagator is a 2-body. This is perfect. We don't want orbital perturbations. We will change the value of the semi-major axis to 15,000 kilometers and its inclination to 0 degrees in order to be in an equatorial plane. This is simple for visualization, and the true anomaly will be to 30 degrees. And on the 3D graphics page, we will go to the model page and increase the maximum viewing distance to a maximum value to be able to see the label from whatever zoom we are using in the 3D graphics window. We'll click OK now, and we will go to the object browser and double click on the interceptor. We will this time use a propagator called Astrogator, and we will select the initial state segment here on the left. Make sure to select the coordinate type drop-down menu to Keplerian, input the same semi-major axis as previously entered, select the same inclination. We know that the eccentricity value here is close to 0, so no worries about it. And the true anomaly value is 0 here, so leave it this way because we want a different true anomaly to show how to do an RPO in this case. We can go to the propagate segment, select the ellipsis button here, select the Earth point mass propagator to not take into account the orbital perturbations. And for the trip value of the duration stopping condition, we will input 2 hours. And we'll run this mission control sequence by clicking this button. Then we can go to the 3D graphics model page here, increase the all value to the max value, and we will click OK. So we can see our two satellites in the same orbital plane, but not the same true anomaly as it seems. But in order to see that more precisely, we will open the properties of the 3D graphics windows with this button here on the top left corner. We will go to a vector page, and we will go to the angles tab of this vector page and click on the add button. We'll make sure that the filter by drop-down menu is selected to all objects, and we will go to the Earth object and click the create new vector to create a new vector called Interceptor, and with a destination point that will be the interceptor's object center, and a reference system that will be the Earth fixed system. And we'll click OK. And we'll repeat the same operation for a two target vector with a destination point to the target object center and a reference system to the Earth fixed system, and click OK. And now we can create an angle here with this create new angle button that is a between vectors angle named initial, just like in our theoretical part of this video. And the from vector will be the Earth, and just go up a little bit on the right and select two interceptor, and the to vector will be the Earth and to target vector, and we'll click OK. And now we can select the Earth on this window and phi initial angle and click OK, and click OK on this properties window. And now we can see the famous phi initial angle that we were talking about on the theoretical part. So this is the delta between the target's true anomaly and the interceptor's true anomaly, and it is of 30 degrees, just as expected, because the interceptor's true anomaly is equal to 0 and the target true anomaly is equal to 30 degrees. And now we will try to store this value inside of STK to reuse it in different functions. So we will click on the Analysis button, click on Analysis Workbench. To open the Analysis Workbench, we'll go to Calculation tab. We'll make sure to select the interceptor as the object and create a new scalar calculation. We'll make sure to select the type of calculation to be a function of x and y, which we will name the initial. So exactly what we just did, except this time we will use a function of a times x plus b times y to illustrate the formula we have in the previous slide, which was phi travel equals the true anomaly of the target, so x true anomaly, which we can find on the orbit menu, classical true anomaly here, and click OK, minus the interceptor true anomaly, the delta between the two. So we'll select orbit, classical, true anomaly, OK. And so we just need to change the coefficient of that's related to the interceptor to -1 to make it a negative and create the difference. Here we'll select inherit dimension to no and dimension to angle, because this is an angle, and we'll click OK. We'll right-click on the phi initial component to create a report and graph, select phi initial as the element, and click Create Report, and you'll see that this is the expected 30 degrees difference. So we can close the report, we can confirm, we can create a new scalar calculation again. We will select the function of x this time, and this will be our phi travel. So our phi travel, if you remember, is the 2 pi minus phi initial formula. So we need a polynomial of third degree here as a function, and x is a scalar, and this scalar is the phi initial we just calculated before, so select it and click OK. And the coefficients here, we need to assign a as the 2 pi, because as you can see on the function here, it's constant, so 2 pi, 6.28 6.28 319 is a good numerical approximation of pi, and b minus 1 because it's minus phi initial, and the dimension shall be inherited from x. It's an angle. So you can click OK. You can create a new scalar calculation here. It will be a function of x and y, and this new scalar is the last one. It's the period of our phasing orbit. So let's call it t phasing orbit, and this function is fraction. It's a quotient. So we'll select this one, and the numerator is supposed to be the interceptor phi travel, so the distance the target has to achieve to reach the interceptor's initial position. And the denominator will be the target's angular velocity. So this can be described as the mean motion, which you can find in the orbit classical mean motion. And in the coefficient, we'll keep 1. And for the output, we'll make sure the dimension is time, and we'll click OK. And we can right-click on the t-phasing orbit report to create a new report to check this period. So this is the period we need to achieve for our phasing orbit to be able to reach in time our correct true anomaly on the new orbit. So we'll close this and remember this value here, and close the analysis workbench, and we'll reuse this value in the properties of our interceptors in Astrogator. So we'll select the propagate segment here, insert a new segment after. It will be a target sequence. We will insert inside of this target sequence a nested maneuver. And this maneuver, remember, has to be retrograde because we want to slow down our satellite. We want to decrease its energy, right? Because we have a lower semi-major axis. So we'll go to anti-velocity vector in the attitude control here, and we will click the target icon here to make sure we can use this thruster. And then we will make sure to select the maneuver segment, click on results, open the menu of the Coplanar elements, select the orbit period, click on the right arrow, and click OK to make sure this is a constraint we can set up. So we go to the target sequence, double click on the differential corrector. To open its properties, we will make sure that we use our thrusters. So we click on use. We'll make sure that we want to reach a specific orbit period. So we click on use here on the equality constraint of the orbit period, and then we double click on the desired value, and we will input 16,749.4. Right? Right. No, the 59. Excuse me. Dot 4. Now we can click OK. We'll make sure to run active profiles when running the target sequence to make sure we can find a convergence. And now we will click this last segment here, add a propagate segment called phasing orbit. We'll change its propagator to the Earth point mass to not take into account orbital perturbations. And we will add a new stopping condition called apoapsis to stop at the apoapsis. And we will select the duration condition and delete it. And we will change the color by double clicking here to red. And we will simply run the entire mission control sequence. And here we found our value for the delta V. So we can close this and we can go back to the properties. We can go to the target sequence, click apply changes to be able to copy this delta V value. Make sure that you run nominal sequence now that you have a delta V. Click on the maneuver, copy this, click on the phasing orbit, insert segment after, maneuver. You can paste the delta V here. You can see that here we have attitude control along the velocity vector, so we are prograde, so this is perfect. And we can insert a new propagate segment, rename it, let's say, to new, and change the color to yellow, and we can run it again. And here we have the visualization of our maneuvers, and we're going to start the animation to see what happens and if our phi initial reaches 0, our objective. So we will increase the time step a little bit, and we see that our interceptor is reaching final orbit, and our phi initial is, well, decreasing a little bit because I forgot to take the Earth point mass, I think, in the other last prop to new, yeah. So I'll simply put Earth point mass to not take into account for perturbations. And here we have 0. Finally, we can see from top our interceptor making a first maneuver to enter the phasing orbit with a lower semi-major axis, and once it reaches the apoapsis of this new orbit, it will perform prograde maneuver to get back into the original orbit parameters, but with a new true anomaly which reaches the same true anomaly as the target. As you can see here, the Earth initial is equal to 0 degrees, as expected. Thank you for watching, and I hope you enjoy discovering more about basic rendezvous and proximity operations.